So we're going to set up a system of equations for 31 using our exponential function. I'm going to plug in my first point, and I'm going to plug in the second point. Well, b to the 0 is 1, so that means 5 equals a. I can take that and substitute it in for this a. Divide by 5. We get 3 equals b. So our equation is 5, 3 to the x. Now for b, we're going to actually have to solve two equations in two variables, because when I plug in my 1 and I plug in the 3, there's nothing that simplifies just like this one did to our first answer. I want to solve this first equation for a so I can substitute it in here. So 20 divided by b equals a. I'm going to substitute that into the other equation. I can reduce my b to the third divided by b. We get b squared. Divide both sides by 20. When you do that, these cancel. So 50 divided by 2 is 25. And when I square root both sides, I get 5 as b. You cannot have a negative b. So our equation is going to be 5 to the x, but I need my a. I'm going to take b and plug it back in here. So 20 divided by 5 equals 4. For 32, I'm going to look at the pattern of our data. So I notice the x's go up by 1, and my y values are multiplied by 4 each time. So that means it's exponential. Because it's multiplied by 4, that's my b. I can figure out what a is by plugging in one of these points. This one's easiest. So 4 equals 4a, so a is 1. So this is just 4 to the x. Now for this part, the second one, I notice these go up also by 1, and I'm adding 5 each time. So that's linear. And a linear equation is y equals mx plus b, where 5 is my slope, so y equals 5x plus b. b being my y-intercept, I can find this value when it's 0 and subtract 5. Or I could plug this in to our equation here and solve for b, just like I did for this first one. This b and this b have nothing to do with each other. It's just the notation that we use for the different symbols for the equation. This b is your growth factor in an exponential. This b is your y-intercept for a linear equation, for a line. For this third one, our x is multiplied by 2, and our y's are going up by a constant of 1, so that's a logarithmic function. This is my base. We have log base 2 of x. Okay, so for this fourth one, I'm not going up by a constant adding value. I'm not going up by a constant multiplying value. And my x's are going up by adding 1. So let's see. If I subtract 1 minus 0, I get 1. 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7. Then if I subtract 3 minus 1 is 2, 5 minus 3 is 2, and 7 minus 5 is 2. So that's quadratic, because the second level of differences are equal. So my equation is y equals x squared, because if I look, each of these x's, square 2 you get 4, square 3 you get 9, square 4 you get 16. For this one, it looks like the y values I can multiply by a half. So that means it's exponential, and b is a half, and this gives us our a. So 400, 1/2 to the x, because a is our initial value when x is 0. This one gives it to us in the chart. So for this last one, my first thought is it could be logarithmic, but I skip 1 and 2 and 3 and 5 and 6. So it's not logarithmic, because that would have to go up by each multiple here. And this is plus 4 and plus 5. So that's not going to work. So how else can I relate my x's to my y's? It looks like if I square root each x, I get these y values. So this is a radical, and it's y equals square root of x. Okay, so for 33, again, we're not going to use our calculator. It's a non-calculator problem. Looking at our table of values, 50 times 3 is 150. 150 times 3 is 450, so it's exponential. Here's my a, it's my initial value, and I'm increasing by a rate of 3 to the x. So after 9 hours, we will plug in 9. So this gives us 50 times 19,683. Multiply that by 50. These first two are non-calculator problems. C is much easier to do with a calculator. So I used a calculator to calculate this.